classes we have discussed about the magnetic effect of current, that is a magnet experiences a force in presence of a current carrying conductor, from which we have inferred that a current carrying conductor produces magnetic field. Now the reverse effect, we are going to discuss the reverse effect, that is if in a magnetic field we place a current carrying conductor, then that conductor experiences a force. And we have already told that current means moving charges. That means from here we can conclude that moving charge or charge in motion experiences a force. And from here we are going to discuss Lorentz force. Today our topic is Lorentz force. What is Lorentz force? Lorentz force is the force experienced by a charged particle. Rather we can say by a moving charged particle in a region where both electric and magnetic field exists. That means if in a region there is electric field as well as magnetic field, then if a charge enters in that region with a velocity, then that charge experiences a force, and that force is called the Lorentz force. We already know that a charge, whether it is rest or in motion, experiences a force in an electric field. If there is an electric field of intensity E, then a charge experiences a charge particle of charge Q experiences a force Q into E. We know that E is the intensity of electric field, then the E means that capital E, which is the intensity of the electric field, means that unit positive charge, force on unit positive charge is capital E. Therefore, charge particle of charge Q, force on charge particle of charge Q is Q into E, and that is called electric force, or we have called that Coulomb force, right? And a moving charge moving with velocity v in a magnetic field B also experiences a force, and that force is equal to Q into V cross B, and that is called the magnetic force. Thus we can say the total charge or net total force or the net force experienced by the charge particle of charge Q moving with velocity V in presence of both the electric field E and the magnetic field B is F is equal to the Fe plus Fm, that is Fe means electric force and Fm means magnetic force, which is equal to Q into E plus Q into V cross B. Now Lorentz force. What is Lorentz force? Lorentz force is the force experienced by a charge particle of charge Q moving with velocity V in both electric and magnetic field is the Lorentz force. That means if in this region there is a electric field of intensity E and also there is a magnetic field of intensity B, and in this region a charge particle of charge Q is moving with velocity V, then this charge particle experiences a force due to this electric field, and that is equal to Fe, and Fe is called the electric force or Coulomb force, which is equal to Q into E. And due to the presence of the magnetic field, the charge particle also experiences a force that is called the magnetic force. Fm is equal to Q into V cross B. Therefore, the net force charge particle of charge q moving with velocity v in a region or in presence of both the electric field E and magnetic field B experiences a force, or the net force experienced by the charge particle is F is equal to Fe plus Fm, and this force is called the Lorentz force. This force is known as Lorentz force, and which is equal to Q into E plus Q into E cross B. That means you can write this as Lorentz force F is equal to Q into E plus V cross B. We have discussed in detail the electric force in electrostatics. Now our main discussion will be on the magnetic force, which is Fm is equal to Q into V cross B. Now the magnitude of the magnetic force, Fm is equal to Q Vb sin theta, where theta is the angle between the V and B. V is the velocity and B is the what? Magnetic field, intensity of magnetic field. And see here the direction of this force. What will be the direction of the magnetic force? The direction of the magnetic force is perpendicular to the plane containing V and B. That is containing the velocity vector and the magnetic vector, and it is given by the right-handed screw rule, right? Therefore, this Fm, if see here, if V is equal to 0, then what happens? If V is equal to 0, then Fm is 0. What does this mean? This means that charge particle at rest does not experience a magnetic force. That means if a charge particle is at rest in a magnetic field of strength B, it will not experience a force, right? Number one. Number two, if V is parallel to B or V is anti-parallel to, V is parallel or anti-parallel to the direction of the magnetic field, then also Fm is equal to 0. V parallel B means theta is equal to 0. V anti-parallel to B means theta is equal to 180 degree. In both cases, sin theta is equal to 0, sin 0 is equal to 0, and sin 180 degree is also 0. Therefore, Fm will be 0. That means no force experienced by a charge particle moving parallel or anti-parallel to the direction of the magnetic field. That means if a charge particle is moving along the magnetic field, or is moving opposite to the magnetic field, just opposite to the magnetic field, then the charge particle do not experience any force. It will remain moving in its original path. Third case, which is very important, our further discussion will be on this case. A charge particle Q moves at right angle to the magnetic field. V is perpendicular to B. If V is perpendicular to B, that means a charge particle is moving normal to the direction of the magnetic field, then this Fm is maximum. The force experienced by the charge particle will be maximum, and that will be Q Vb sin 90. That means Q into V into B. This is the maximum force experienced by a moving charged particle in a magnetic field of strength B. Is it clear? Now, from here we can define the magnetic field strength, that is B. From here we can define the B, magnetic field. See here, B can be written as Fm divided by QV sin theta. Now if Q is equal to 1, V is equal to 1 and theta is equal to 90 degree, then B is equal to Fm. Q is equal to 1, V is equal to 1, sin 90 is 1. That is B is equal to Fm. That means a magnetic field at a point, may be defined as the magnetic force experienced by a unit charge moving with unit velocity at right angle to the magnetic field. Magnetic field at a point may be defined as the magnetic force experienced by a unit charge moving with unit velocity at right angle to the direction of the magnetic field. Is it clear? This is the definition of magnetic field. And what will be the dimension of the magnetic field? Dimension of magnetic field. From here you can derive. That means dimension of force divided by dimension of charge divided by dimension of velocity. Sin theta is dimensionless. Therefore, m t to the power minus divided by q is it and v is l t to the power minus 1. From here we can write what? L cancels out. That means you can write m l to the power 0 t to the power what? T minus 1, that is t to the power 0 in the denominator, therefore t to the power minus 2. And I here, that means I to the power minus 1. This is the dimension of the magnetic field or magnetic induction. And from here you can also give the SI unit kg second to the power minus 2 ampere to the power minus 1, which is Tesla. Just remember this thing. This is called Lorentz force. Here, this force is called Lorentz force. This is the expression for Lorentz force. Lorentz force is the net force experienced by a charged particle in electric and magnetic field. Right? If there is no electric field, then there will be only magnetic force, that is Q, F is equal to Q into V cross V. If there is no magnetic field, then the charge will experience only Q into electric force. If charge is moving parallel or anti-parallel to the magnetic field, then there will be only electric force. If charge is at rest, then there will be only the electric force. There is no magnetic force. Right? These have to be remembered.